Hey everyone, today we're going to be solving LeetCode 437 path sum 3. Now let's take a look at the problem. We're given the root of a binary tree and an integer target sum, and we want to return the number of paths where the sum of values along the path is equal to target sum. And it's important to note that the start of the path doesn't have to be at the root and the end doesn't have to be at a leaf. It can just be any path along our tree, but it has to go downwards and it has to be contiguous. So taking a look at this example, we have target sum of 8, so we get this 5 and 3 path, we get this -3 and 11 path, and we get this 5, 2, and 1 path. Now, let's think about how we're going to solve this. You might be first tempted to go for a recursive solution where every time we get to a new node, we start the path if it hasn't already started, and otherwise we continue it. But if you do try this, you'll see this is my first attempt. There's going to be a lot of recursive calls. So each time, if it's not been started already, we're doing these two calls. And then we're also doing these two calls regardless every time. So it's going to have a pretty bad runtime compared to the other solution that we're about to talk about. Right? We have this solution with a 400 millisecond runtime and this one with only 54. So let's think about how we can do this, and the important thing to think about is that we're going to have to store our results along the way somehow. So let's think about this logistically, right? So let's say we have the root right here, right? And then we have some nodes, and let's just say we have a bunch, right? We're going along a path. So just say we're depth first searching, and then we get to here, right? So if we do a depth first search and we track our sum, this whole sum is going to be like a current sum, right? However, it's important to note that we're actually going to have a bunch of little sums over here. So we'll have this sum when we're only at this point, and then when we're at this point, we'll have this sum. Now, it's important to note that if we're going for a target sum, we can actually use the previous sums along the way to find our solution. So let's say, for example, we're looking for a target of 8, right? Target is 8. And let's say that this entire thing, right, has a sum of 18. And this right here, just these two, has a sum of 10. Well, if this has a sum of 10, right? Sum equals 10. If this portion has a sum equal to 10, then and the whole thing has a sum of 18, that means everything that we didn't include right here has a sum of 8, which is going to be our target. So essentially what we can do is we can just keep track of the current sum, which will be x, and if x minus target is a sum we have seen previously in our depth first search, then we can say that we've actually found a path, right, that has the target sum, because our total sum minus the subset sum that we found is going to be our target, if that makes sense. Now, there's one more important caveat to know, and we can't just keep a set of sums that we've seen, because imagine this situation, right? So imagine we're doing this. Imagine we have a target sum just like before, or a total sum right here, 18, and our target is 8, right? Target is 8. Now let's say that we've seen the sum here, right? Like we were talking before. Let's say this is a sum of 10. And let's say that this right here is also a sum of 10. Well, then we actually are going to get two answers. The first one will be all of these elements right here, and the second one will be all of these elements right here. So we actually not only have to keep track of the sums that we've found along the way so far, but we also have to keep track of how many times we have seen that sum, because this is going to give us two different ways to create a sum ending here, or a path ending here with target 8, right? So let's think about how we're going to code this up. Okay. So the first thing that we're going to want to do, like we're talking about, is keep track of the number of ways we've gotten a current sum from the root in the in the current DFS, right? DFS path. So we're going to use a default dictionary because that's going to initialize everything at 0, and it's easier just to use plus equals instead of checking if it exists. And it's also important to note that we're going to initialize sums of 0 equal to 1 because there is going to be a way that we can make a path with a sum of 0, and that's going to be by not using any nodes, right? This is going to be, before we even start with the first node, we do have a way to make a sum of 0. This is important to note because, like, for example, if our first node is equal to the target sum that we're going to get, we're going to not have 0 in the hash map originally, which is going to cause us some problems down the line. That's just one example of a case where this will negatively impact our algorithm and make it not work. So next, what we're going to do is we're going to just make a simple recursive depth first search. So it's going to take a tree node, right? And it's going to take the current sum up to this point from the root, right? And it's going to return an integer, which is the number of paths that we've found. And every time that we return back up, we're going to be adding both branches together. So base case, if it's null, we're just going to return 0 because there's obviously 0 paths starting from this null node, right? Next, we're going to update the current sum, right? We don't really need a comma for this. Current sum plus equals node.val. Now we get to the trickier part. So what we want to do is we want to count all the paths like from this node. So what we're going to do is, like, when we get to this 3, we're first going to count this blue one, and then we're going to check both of the subtrees if they also have paths, and then return this blue one plus whatever we find in the subtrees. Okay, so what we're going to do is initialize paths to be 0. This is what's going to be returned. So number of paths found. And firstly, we're going to have, like we talked about earlier, we're going to have all of the paths if we have cur sum minus target sum, right? Just like we talked about earlier. We're going to have that hash map that keeps track of the complement like we talked about earlier. So for example, if we're at 18 and we've seen the sum 10 twice before, then we're going to have 2 ways to make that target 8 that we were looking for. Now, what we're going to do is we need to update the hash map, right? I'll just add a comment here to make it look good. So we're updating the hash map, but we want to do sums of cur sum plus equals 1, right? We just want to mark that we've seen this sum before and increment the count of it by 1. And now we have to recurse to each subtree to count the number of paths down there. So we're going to do paths plus equals, right? Because we want to tally this all up and search from the left, and then also we want to search from the right. And then what we're going to do is when we recurse back out, right, we need to take the current sum out of sums because we're done with this tree, right? Let's say, for example, that we were at this 3, right, and we returned back up to this 5. Well, when we're done with this 3, we need to take 18 out because we're going back to 15, right? So we haven't seen 18 along this path because we're going down a different path. So what we're going to do is we're going to do sums of cur sum minus equals 1, right? So we're adding it to the hash map. We're recursing where it actually matters, and then we're removing it back out from the hash map because we're done with this branch. I don't want to say removing it from the hash map. We're decrementing the count in the hash map, but you kind of get what I mean. And then all we need to do is return paths because we've counted the one considering every node before to get this path, and then we've also counted both of the subtrees. So we've counted everything, so we're just going to return paths back out. And so this will tally up all the way every time it recurses back to the root. So all we need to do now is call it from the base case, which is going to be DFS from the root, and the current sum is going to be 0. So let's try submitting that and see what we get. And as you can see, it works pretty well. So thank you for watching. I hope you found that helpful, and goodbye.